Papa Suyu, chocolate cream, the real Korean chocolate uyu.
What the Milo? Baru Milo Aktif Biskuit. Nikmati energi Milo kesukaanmu di setiap gigitan.
So what is ClickUp? ClickUp is an all-in-one productivity software where you can manage everything and anything related to
Part paling males itu nyisir, karena pasti ada aja gitu rambut yang rontok. Tapi setelah pakai pentin
So now we're going to talk about virtual memory. So now we're going to talk about virtual memory, trying to make the software. So first of these problems is what happens if you don't have enough. So now we're going to talk about virtual memory. And virtual memory is one of the coolest parts of the computer's architecture because it really combines the idea of trying to make the software work well with what we can do in hardware. So in talking about virtual memory, we're going to start off with three problems. And the first of these problems is what happens if you don't have enough RAM in your computer. And this problem was really the motivation for virtual memory in the first place. It used to be that RAM was really expensive, and so you wanted to use it very efficiently, and you needed to be able to run programs even if you didn't have enough memory. Now these days we tend to have tons of RAM in our computers, so this is much less of a problem. In fact, if you run out of memory on a computer today and have to use virtual memory as a result, it generally slows things down so much that it's almost not worth doing. But there's some other problems that we have as well. So we have holes in our address space. If you run multiple programs together and then you quit some of them, you leave these chunks of memory that are unavailable. We also have problems with programs writing over each other. So remember in MIPS, we promised each program that it could access 32 bits of address space, and so if you have two programs that both write to address 1000, what happens? Do they write over each other? How do we keep them from crashing each other? So after going through those problems, we're going to talk about what virtual memory is. And basically, it's just indirection. So virtual memory is the idea that we take the address that the program uses and we map it to the real address in memory. And by having this mapping going back and forth, we can do a lot of interesting things about controlling where the memory goes and how we use it. We're going to show how this indirection solves the problems above, and we're going to talk about the idea of page tables and translation, which is how we store the mappings and how we actually do the mappings. Then we're going to talk about how we implement virtual memory. So where do we store these page tables, these mappings between our addresses, and how do we make them run really fast? So we're going to make them run fast by adding hardware to the computer to make it faster. And then finally, we're going to talk about how virtual memory interacts with caches, because caches are an important part of making memory faster, and we want to make sure that virtual memory doesn't mess that up.
So, research shows that 70% of startups offer some remote work and they prefer hiring virtual assistants.
So let's start off with three problems that we have with memory, as we've described it so far in MIPS. So the first of these problems is, what if we don't have enough memory? So remember, MIPS gives each program its own 32-bit address space. When we do load word or store word, we specify a 32-bit address. So that means that programs can access any byte in their 32-bit address space. So the MIPS ISA makes this promise that every program can access 32 bits of address space. Now, how much memory can you access with 32-bit addresses? Well, you can access 2 to the 32 bytes or 4 gigabytes of memory. So theoretically, you can access 4 gigabytes of memory. So theoretically, we've promised each program to get 4 gigabytes of space. In practice, the operating system reserves some of this, so it's really closer to 2 gigabytes. But for simplicity, we'll just look at giving each program its full 32-bit address space or 4 gigabytes of memory. Okay, so here's the problem. What if you don't have 4 gigabytes of memory in your computer? So go back 4 years. Nobody had 4 gigabytes of memory in their computer. Now it's pretty common, but what did people do before they had this much memory? So let's take a look at the problem here. Here's the 32-bit address space that MIPS promises. So MIPS promises a program that can access any byte within this range, from all zeros to all Fs. So any byte in 4 gigabytes of space. Now say I have a computer which only has 1 gigabyte of memory installed. So that's a 30-bit RAM address space. It's a quarter the size of this. We promised 4 gigabytes, but I've only got 1 gigabyte of memory in my computer. So what happens here? Well, if I go to access the first part here in MIPS, that's not a problem. Access the first part of memory. Second part, okay. Third part, okay. Now, but what happens when I access this here? What happens when my program tries to use more than the 1 gigabyte of memory that's in my machine? Well, there is no memory here. So if I don't have virtual memory, I'm going to go ahead and crash. There's no way to access this part of the address space. If I access it, the program will crash because there's no physical memory sitting there. So this is the first problem with memory. We promise each program a 32-bit address space, but the actual amount of memory address space we have depends on how much RAM is installed. So here's another program, holes in our address space. So when we have programs running together, multiple programs, they share the memory, and where do we put them? So here's our 32-bit address space. Now we have a computer that has the full 4 gigabytes of memory, full amount of memory it can. So we've got a bunch of programs here. So program 1 wants 1 gigabyte, program 2, 2, and program 3 wants 2 also. So programs 1 and 2 fit together. So here I'll go ahead and run program 1 and put it into the memory, run program 2, put it into the memory. They use 3 gigabytes of memory together, so I still got 1 gigabyte free. Okay, no problem. Now what happens when I quit program 1? So when I quit program 1, I've freed up a bunch of space here. So now I have 1 gigabyte here and 1 gigabyte here, but I can't run program 3. Even though I have 2 gigabytes of memory free, and program 3 needs 2 gigabytes of memory, it's split up. Got 1 gigabyte here and 1 gigabyte here. I don't have anywhere I have 2 gigabytes of memory in a row where I can run program 3. So what this is called is memory fragmentation. I get these holes in my memory due to the order in which I ran programs. Now let's look at another problem with the memory. How do we keep our programs secure? So each program can access any 32-bit address. What if multiple programs access the same address? So let's take a look at an example here. We're going to have 2 programs that are both going to issue this instruction, store word R2 1024 at R0. So this instruction is going to write to address 1024. So here's one program, here's another program. So program 1 is storing my bank balance. It's going to go store my bank balance at address 1024, and here it is. So it's gone and written my bank balance into memory. Now program 2 is going to store my video game score, and well, it's going to store it to address 1024 as well. So here I've run 2 programs, both of which are writing to address 1024, and they've overwritten each other. So what happens here? Well, they're corrupting each other. Because we don't have any way to separate what memory they're accessing, they're both trying to access memory 1024, which is perfectly legal, they're going to bump into each other. So we don't have any way to keep programs separate, so we can cause this corruption or crashes. And this is why programs and computers crashed an awful lot a long time ago, because we weren't using virtual memory. So what were the problems with memory we looked at? We saw that if all of the programs have access to the same 32-bit memory space, they can crash if we don't have 4 gigabytes of memory installed, because 32-bit addresses promise 4 gigabytes. They can run out of space if we run multiple programs, because we get these holes in our memory. And we can corrupt each other's data. So if they both write to the same address, they corrupt what's in their address. So how do we solve this? Well, obviously this lecture is about virtual memory, so it's going to be with virtual memory. But what's the key here? Well, the key to the problem was this thing I set up here about the same 32-bit memory space. So the reason we're having all these problems is that we have this same memory space for everything. Every program has the same memory space, and our actual RAM has the same memory space. Because it's all the same, we don't have any flexibility. So, if we can give each program its own virtual memory space, then we can start solving these problems. So that's what virtual memory does. It gives each program its own virtual memory space and then maps it to the physical memory. So what we're going to do is we're going to separately map each program's memory space to the RAM memory space. So with virtual memory, we have a whole bunch of these memory spaces. We have a memory space for each program called its virtual memory space. We have a memory space for the RAM called the physical memory space. And then we're going to have this map in the middle that maps the program memory spaces to the RAM memory spaces. And that's really all virtual memory is. What we're going to talk about in this lecture is all the cool things you can do with it. Now, you can see here how by having this mapping we can solve some of these problems about holes in the memory and corrupting. But what we can also do is we can move data to disk. So if we run out of memory, we can map some of the program's memory space. Instead of to RAM, we can map it to disk. So we can use our hard disk as memory. That's what the term virtual memory comes from. It's not real memory, it's virtual memory. So the key here is the mapping that gives us the flexibility in how we use the physical memory. Now here's a question about shared address spaces. So which of these things down here is not a problem if all programs share a 32-bit address space and we have less than 4 gigabytes of memory? Well, it's really this one in the middle, can't reach the full memory range due to 16-bit immediates. We saw that we can make a 32-bit immediate by using 2 16-bit immediates and 2 instructions. So we can create that, but the other ones are the problem. Reading some addresses will cause a crash if we don't have 4 gigabytes of memory. Programs can overwrite each other's data if they have the same address space, and they may not fit together. We may get these fragmentation or holes if they're all using one memory space.
English is my second language. As a vlogger, I deal with social media a lot, which is actually fun for me, but I will say sometimes it's challenging. For my social media, I have to think about captions a lot that sometimes require me to write in English and reply to emails in English.
Alright, so now let's talk about what virtual memory is. And I'll give you a hint here. Virtual memory is all about indirection. Remember, we mentioned that there are different address spaces for the program and the memory, and virtual memory is about the indirection pointing between them. So, virtual memory is a layer of indirection. And this comes from the general idea that any problem in computer science can be solved by adding indirection. If you got a problem, add a layer of indirection and we can almost always solve it. Let's take a look at how this works in virtual memory. So without virtual memory, we don't have indirection. The program address that the program uses in MIPS is exactly the same as the RAM address. So if the program tries to load from address 1024, it's going to look for RAM address 1024. So here's our 32-bit address space the program guarantees, and here's our 32-bit address space if we only have 1 gigabyte of RAM in our computer. And we saw before these addresses are fine. Address 0 is going to map over here to 0, 1 to 1, etc., all the way through the first gigabyte. But what happens is when we start using addresses that are beyond the first gigabyte, they don't have anywhere to map to. So with this direct mapping here, we're going to crash if we try to access more memory. So virtual memory is going to solve this by adding a level of indirection. So in virtual memory, we're going to take the program addresses and map them to a RAM address. So instead of going one-to-one like this, we're going to have a slightly different mapping. So here's virtual memory, and it's going to do this mapping. So we have our 32-bit program address space. We still only have 1 gigabyte of memory installed in our computer, but now we're going to have this map in the middle. And this map is going to provide exactly this indirection that I was talking about before. So let's see how this can work with the map. So here's address 0. Where's it going to go to? Well, we look in the map. The map sends it over here to RAM address 1. Okay, why not? It can map it to anywhere it wants. Here comes the next one. It maps it up here to address 0. Okay, sure. Here comes the next one. It maps it into here. Now we've done the same thing we've done here. We've mapped everything. It's not the same mapping, but it's just a mapping. What happens now when we access this next piece of data? Well, now that we have a map, this next piece of data can say, hey, it's not in memory. It's somewhere else. It's on the hard disk, for example. So our program's not going to crash. It's going to know it has to go get the data from the hard disk before it can continue. So what virtual memory does here is it gives us flexibility in how we can use our memory here. So this mapping allows us to use our memory in a more flexible way. So let's take a look at how virtual memory solves these three problems that we looked at before. So here's our same 32-bit address program space and our same 1 gigabyte 30-bit RAM address space. So we have 1 gigabyte of memory installed, and MIPS promises 4 gigabytes of memory space to every program. Now we've got this map in the middle, and we've got a disk over here where we can put stuff that doesn't fit. So let's take a look at this. We're going to map some of the program's address space to disk when it doesn't fit, and when we need it, we'll bring it into memory. So here we are with virtual memory, and remember the program address is going to map to the RAM addresses. So the program goes and tries to load address 0, goes to the map says, okay, address 0 is over here, no problem, you can access it. So the virtual memory has mapped program address 0 to RAM address 1. Now the program wants to access address 1. Okay, so we go into the map, and the map goes over here, and it maps address 1 to RAM address 0. No problem. Go to program address 2, it goes and maps it down here. That's fine. Now here's where it gets fun. So now we try to load the program address 3, the next one here. And this one doesn't fit into the amount of memory we have here. So this part here took up our first gigabyte of memory, now we're trying to load something beyond 1 gigabyte. What's going to happen? Well, when you do this, you go to the map, and the map says, hey, I don't have any more space in your memory that's installed in your computer for this data. What am I going to do? But because I have this flexibility, I can move the data around. So it's going to go put it on the disk now. So virtual memory is going to find the oldest piece of data in memory. In this case, it's this 01 here. It's going to go and move it out to the disk. This is called a page out. It's taking this page of memory and writing it out to disk. Then it's going to go and update the map. So the map here still says that this is in memory. We're going to update that map to say, nope, it's not in memory, it's on disk. Now that we've freed up this memory here, now we can go ahead and access program address 3 here and put it in the memory that we freed up from that earlier data. So by having this mapping, we can use our disk to give us the illusion of unlimited memory. So as long as we have 4 gigabytes of space on our disk, we can always give every program 4 gigabytes of memory because we can do this mapping and put as much of the data on the disk as we need to. So that's how virtual memory solves the problem of not enough memory. Now here's a question about virtual memory performance. What's going to happen to the program performance when the data it needs is on the disk? Well, we're going to get really bad performance. Reading from disks is slow. Disks are thousands of times slower than memory. So if we have to put the data on the disk, it's going to slow down our performance enormously. This is why people tell you if you buy more memory for your computer, it'll run faster, because you'll have less time you have to go to the disk to access data. Now let's take a look at how we solve problem number 2. This was the holes in the address space. So remember, we quit program number 1 up here, and it left these two 1 gigabyte holes, and we decided we couldn't run program 3 because it didn't fit into either of these holes. Now we're going to have this map so we can be more flexible in how we use the memory. So here's program 3 and program 2. Here's program 2's map, and as we saw, program 2 was mapped into the middle chunk of memory here. But with virtual memory, we can map program 3 wherever we want. So here's program 3's map. We're going to take the first part of program 3 and we'll map it up here. We'll take the second part of program 3 and we'll map it down here. So now program 3's memory is split around programs 2's, but it doesn't matter because this mapping allows us to map any part of program 3's memory to any part of our real memory. So we got this added flexibility from having these mapping, and now we could fill up these holes and really use all of our memory. So with each program having its own mapping, we can put our data wherever we want, and we can be more flexible about using these holes in memory. So let's take a look at the third problem here, keeping programs secure. So here's program 1 and program 2. And remember what's going to happen. Program 1 is going to store your bank balance at address 1024, and program 2 is going to store your video game at address 1024. So we're going to use maps for them to put them in different RAM addresses. So program 1 has a map and program 2 has a map. Program 1 is going to go to address 1024, and its map is going to send the data somewhere. So in this case, we're sending the data over here to RAM address 1. Okay, so it writes to RAM address 1. Program 2 is also going to try and access address 1024, but its map is going to send the data somewhere else. So in this case, it's going to send it over here to RAM address 5. So now they write to different places because we have these mappings that make sure, even though each one of them is trying to access 1024, they have different mappings that send them to different physical locations in memory, and they don't overwrite. So neither one of them can touch the other one, and we've got this security. They each have their own address space, and they can't access each other's maps as long as we don't map them over each other. So here's a question about program isolation. So we just showed you how you can isolate programs here. Is this always good? If you completely isolate the programs, what's the downside of this? So the downside of this, if you do it entirely, is you can't share data. So programs often share a lot of data. But if I have this mapping where they're completely isolated, they can't share that. Now, we can use the same mapping to enable shared data. So say I have a mapping here that maps part of program 1's addresses down here, and another mapping that maps part of program's 2 addresses right here. Now they can explicitly share that same data regardless of where they need to access it. And this is actually very common. So if we take a look at this here, here's the save dialog box from my mail program, and here's the save dialog box from my web browser. You'll notice these are exactly the same. All of the code and all of the icons and graphics for both of these dialog boxes are the same. So you want these to be shared between each program. So the memory that represents these save dialog boxes, that's going to be shared between the two programs. So we need to make sure they can do this sharing. So save dialog box, fonts, graphics, all those things are examples of data that you want to share between programs.
Get guys! Paket data harganya mulai dari 6.000. 11 November, promo puncak Shopee 11.11 Big Sale. 11 November, 11 November.
Now let's talk about how virtual memory works. And we're going to introduce two concepts here, virtual and physical addresses and some acronyms for them. So how does virtual memory work? The basic idea is we have these separate memory spaces. So virtual memory is what a program sees, and physical memory is the physical RAM in the computer. So when you install memory in your computer or you buy a computer with memory, this is what you're paying for. What the program sees, the virtual memory, this is what the ISA promises. So remember, in MIPS, this promises the virtual address. So if we do a load R4 1024 R0, this is going to access a virtual address 1024. So the MIPS ISA promises a certain virtual memory address space, but the physical memory is what you have in your machine. So if you have 2 gigabytes of RAM installed, you're going to have physical addresses from 0 to 2 to the 31 minus 1. That's 2 billion bytes of memory. So virtual addresses, or VA, we're going to abbreviate them virtual addresses VA, this is what the program uses. And in MIPS, it's a 32-bit address space. The physical addresses, or PA, is what the hardware uses to talk to the RAM. And this is determined by how much RAM you have installed. If you only have a little bit of RAM installed, your physical address space, or your PA, is going to be small. If you have a lot of RAM, it's going to be big. But now we have separate address spaces here. So each program is going to have its own virtual address space, and we have a physical address space for our memory. So how do we make this work? How does a program access memory? So the program executes a load, and the load is going to specify a virtual address because that's the way programs work. So here's our processor, it's running the program virtual address space, and here's our load. So load R3 1024 R0. What's the physical address going to be here? Or sorry, virtual address? Well, it's just going to be 1024. So the processor is going to access virtual address 1024. That's what this instruction is going to do. Now, the computer is going to translate this virtual address to the physical address in the memory. So we're going to have a translation here. This is our map from virtual address to physical address, and it's going to tell us how to get the data over here. So here's the data we want for R3. This map is going to tell us how to get there. So we go ahead and tell the translation, or the map here, we want virtual address 1024. It looks it up in its map. It says, oh, well, virtual address 1024 maps to physical address 2. So it goes over here to physical address 2, and it goes and gets the data. Now, if the data is not in memory, it goes and loads it from disk. In this case, it is in memory, so we're going to take this data here, and we're going to return it. So we took virtual address 1024, translated it to physical address 2, and now we send this back so we get the data. Now we go ahead and do another instruction. This instruction here is going to load virtual address 512. So we go over to our translation, ask it where 512 goes. It says, hey, it goes to physical address 12. So we go down to physical address 12 here, go ahead and get our data, and we send it back. Now we do another instruction. This is an add instruction. It's just using registers, so we don't need to do any translation here. And then we go and we have another instruction. This is going to access virtual address 786. So we go to virtual address 786. The map tells us it's on disk. It's not in memory. Okay, it's on disk. So what do we need to do to get it? Well, we need to load it into memory. So we go ahead and load this data into memory. Once we've loaded it into memory, now we go and update the translation map. Okay, so now we no longer want to translate address 786 to disk. We want to translate address 786 to this location in memory. So we update that to 4. Now when we put in virtual address 786, we get out physical address 4. We go ahead and load it from data, from the memory, and we return the value. So program executes and load with a virtual address. The computer translates it into the physical address. If it's not in memory, we get it from disk. And then the computer reads the RAM using the physical address and returns it to the program. That's how virtual memory works. So a question, what address is located here? So address R12 has the value 1536, and the program issues this load. What location in RAM is going to be accessed? Well, we need more information here. The program is accessing virtual address 1536. That's what this is going to do here. But we don't know what physical address that's going to be. So here's our processor. It's in the program's virtual address space, and we do this load. This load is going to generate virtual address 1536, but we're going to have a map, and the map's going to tell us which physical address it is. Now, if I don't tell you what the mapping here is, you have no idea what location in RAM this address is going to access. So we need more information to know what memory we're actually going to access when we issue this instruction. So here's another question about using too much data. If a program uses more data than can fit into RAM, where does the data go? Well, it's going to go to disk. If it doesn't fit into the memory, we're going to use virtual memory to map it to disk. So here's a load. So this load's going into our table, and we didn't have enough space in memory, in physical memory, for this virtual address. The translation table, the map here, will tell us that it's on disk, and we'll know it's on the disk. And so we can put the data on disk if it doesn't fit into memory. Now we're going to talk about page tables. And the page table is the mapping that keeps track of these virtual address to physical address mappings. And we're going to see in a minute why we call it a page table. So we saw before that we have this map from the virtual addresses to the physical addresses. We're going to call this the page table. What we've seen so far is we had one entry, or one page table entry, for every virtual address. So here we had one entry for address 512, one entry for 786, because we also had entries for all the words in between these as well. So how big is this? So if we need one entry in our page table for every virtual address, and remember virtual addresses are word access, how many do we need? Well, we need one for every word. So that's 2 to the 30 or 1 billion entries. So that means that this table here, for a 32-bit program address space, has to be able to fit 1 billion entries in it. And each one of these entries is pretty big. It has to say what's the virtual address and the physical address, so it's at least 32 bits. So that means this is about 1 gigabyte of memory just to keep track of this page table. So this doesn't sound very good. I mean, we'd have to use up a whole gigabyte of memory just to keep track of the memory for one particular program. So how are we going to solve this? Well, let's talk about page table size. So we need to translate every address. Our programs have a 32-bit virtual address space, and we have to be able to access everything in it, or the programs can't use all their address space. So that's 2 to the 30 words that need page table entries. If we have one entry for every word, it's 1 billion entries. That's way too many entries. Now remember, if we don't have a page table entry, then we can't access that location. We need the page table entry to get the physical address so we can actually load the data. So we have to have some sort of page table entry for every single word in our virtual address space. So how can we make this more manageable? Well, here's what we had before. We had this fine-grained mapping. Each word was mapped in our table here. What we can do is we can have it in bigger chunks. So we divide our memory into chunks, and we're going to call these chunks pages. That's why it's called a page table entry instead of words. So here's what this looks like with coarse grain. So here we have a whole page. So we're saying that virtual addresses 0 through 4095 are going to map to physical addresses, whatever, 4096 to 8191. So now instead of having one entry in our page table map one word, one entry in our page table is going to map this whole chunk of memory. And we're going to call this chunk of memory a page. So in this case, we have these 4 kilobyte pages. So each entry in our page table now handles 4 kilobytes of data. Before we had each entry in our page table handling 1 word or 4 bytes of data. So this is now, each chunk here is 1,024 times larger than they were here, so we need 1,000th as many of these entries. Makes our page table much smaller. So now we're going to do this coarse-grained pages instead. So our page table is no longer going to manage entries for each word, it's going to manage entries for each page. So we have fewer entries needed to cover the whole address space. And here's the example. We had 4 kilobyte pages here. There's also a trade-off. It's less flexible. Before, we could move each word at a time. Here we're going to have to move 4,096 bytes at a time, 4 kilobytes every time we want to move a page. So if we need to move something out to disk to make room, we're going to have to move out 4,096 bytes at a time to make room. So today we typically have 4 kilobyte pages. It's 1,024 words per page. And here's a question about them. How many entries do we need in our page table now that we have 4 kilobyte pages for this 32-bit machine? Well, we need 1 entry for every 1,024 words. It's a 4 kilobyte page. Each word is 4 bytes, so that's 1,024 words per page. So that's going to be 1 million entries. So this is great. Instead of needing 1 billion entries like we did before, we just need 1 million. This is enormously more manageable. So before our page table was a gigabyte in size, now it's going to be about 4 megabytes in size, which is much more reasonable. And in fact, people even go further than this. So today you have lots of 64-bit machines. People are getting very common to use 2 megabyte pages. So in a 2 megabyte page, you get 520,000 words per page. This allows you to cover more of memory space with a smaller page table. So there's a trade-off here. Cover more memory space with a smaller page table, but you have to move a whole page at a time, so you get less flexibility. Now, How do we map addresses within a page? So before this was really easy. You just looked up the word address in your page table and it told you what the physical address. Now our page table tells us that all the addresses in this range map to this range. So how do we look something up? So to do this, we think about our virtual address space and our physical address space in pages. So here are the pages. Here's the first page in our virtual address space. It's address 0 to 4095. The second page, the third page, the fourth page, etc. The same thing for our physical address space. We have pages. Now in this example, our physical address space is smaller than our virtual address space, so it has fewer pages. Now we want to go ahead and see how this translation works. So this translation tells us that virtual addresses 0 to 4095, so that's addresses in this page, are translated to physical addresses 4096 to 8191. So that's saying that this page is translated over here to this page. So instead of pointing to individual words, we're just saying this whole page gets translated this whole page. Now that's fine, but here's a question. What's the physical address for virtual address 4? Well, the map doesn't have an entry for 4, it just has a map for this range. So how do we translate that? Well, the answer is going to be 4100. So all of the virtual addresses in this range are going to be mapped into this physical page here. So address 4 over here is offset by 4 bytes from the start of this page. So we can figure out where this page maps. It maps over here. And then we know that this word is going to be offset by 4 bytes over here in this physical page. So it's going to be 4 bytes off from address 4096. So it's going to be address 4100.
Baru, mie sedap kap kari mercon. Meledak sedapnya. Juaranya kari pedes yang gak pakai ribet.
60.000.
Ih, mahal amat.
Yang hemat, restoran hebat, isi 2.
Kalau gini sih, yuk bawa pulang. Hebat-hebat banget, 6.000 harganya.
So now we're going to talk about address translation. This is the details of how do we take a virtual address and actually translate it using the page table map into a physical address. So what happens if we have a 32-bit machine, just like the MIPS we've been looking at, but it only has 256 megabytes of RAM, and we've got 4 kilobyte pages. So let's take a look at what this looks like. So we have a 32-bit virtual address. That's what our MIPS promises us. So each program can access 32 bits of address space, or 4 gigabytes of memory, but we only have 256 megabytes of RAM. So here's our 32-bit address space for virtual address space, but we only have a 28-bit physical address space. So 28 bits gives us 256 megabytes. So we've got a 28-bit physical address space here. How do we convert between the two of these? Well, that's what our page table is for. Our page table is going to take in our virtual address and convert it to a physical address. So in goes our virtual address, out comes our physical address. Now, we've looked at this and we've seen the page table takes care of pages. So each page is 4 kilobytes of address space, 4 kilobytes of data. And what we've seen here is that each page has 4096 addresses, and these don't get translated. So the lower 12 bits, those are the bits needed to go in the page, tell us which one of the bytes in each page we have, those just go straight through. This is what's known as the page offset. So remember, we saw this before. We had a page over here, and we had this offset in the page. And the offset stayed the same when we did the translation. Stayed the same from the virtual address over here to the physical address. We had this same offset in here. So the page offset, which for 4096 byte pages is going to be 12 bits, that stays the same and doesn't get translated. So what that means is that the remaining 20 bits of the virtual address is going to go into the page table and is going to get translated to 16 bits out here of the physical address. Okay? So this part here, the page offset, that stays the same because it's the same in the physical and in the virtual and physical pages, but which page we point to goes through the page table and changes. Now we have a smaller physical address, so fewer physical pages, because we have less physical memory than we do virtual memory. There's some terminology here. This is known as the virtual page number. It's the page in the virtual address. This is the page offset within that page number. So this over here is virtual page 0, and the page offset here is whatever this was. In the example we had before was 4. This over here is the physical page number and the page offset within that. So over here, this was the second physical page, but it had the same offset of 4. So important things to remember: the virtual address is translated in the physical address. Some parts of the virtual address are the page number, tells us which page it is, and some parts are the page offset. The page offset doesn't get translated because it's the same offset in the pages in the virtual and physical address, but the page number does get translated. So let's take a look at this. So in our virtual address space, we have all these pages. Divide our virtual address space up into pages. And this is our full 32-bit virtual address space, so 0 to 2 to the 32 minus 1, 4 gigabytes of space. We have within each page, to find a word, we need to know both which page it is, which virtual page, and what the offset is within that page. Now the page offset, these are the last 12 bits of the address, and they tell us where we are within the page. To know which page we're at, well, we need to know is it virtual page 0, 1, 2, 3, etc. That's the other 20 bits of the address. So the virtual page number parts of the address tell us which page we're on, and the page offset bits tell us where we are within the page. Now, we haven't actually changed anything here. For the virtual address space, we're just looking at the address in terms of pages. It's still going to whatever this was, address 4. We're just now thinking of it as split into two different parts of the address, the virtual page number and the offset, and the only reason we have this offset is because we chose a 4 kilobyte page. Now, when we look over here in the physical address space, we have the same thing with our pages here, and we've got a smaller space here because we only had 256 megabytes of memory. And we have the same two questions to ask to figure out where this data is. Which page is it in, and what's the offset within that page? Now, as we saw before, the page offset bits don't change. So these 12 bits are going to tell us where we are within the page, what the offset is, and these are the same as the offset bits we had in the virtual address space because they're within a page, but which page we're at is going to change. So here we have physical page 0, 1, 2, and we can see that now we're in physical page 1. So we'll get there by looking at our physical page number bits. These bits are going to tell us which physical page we're in. From the DRAM's point of view, this is just a different way of looking at the memory. It doesn't care, it just needs to know the address. The reason we've divided this up is when we do translation. So translation is done in page-sized chunks, so we don't pay attention to the offset. We're going to take the virtual page number and we're going to translate that into the physical page number. So we're not going to translate these page offsets, just the virtual page to the physical page. So in the example here, we're taking virtual page 0 and we're translating to physical page 1, but the offset bits stay the same within the page. All right, so here's a question about virtual versus physical page number bits. Here's our setup. Remember, we've got 12 bits of page offset that don't change. The offset's the same in the virtual and physical address, and the rest of the bits are translated through the page table. So in this question, in this example, why do we have more virtual page number bits than physical page number bits? So why do we have 20 bits in the virtual address and only 16 bits in the physical address? Well, the reason for this is the virtual address space in the example was larger. Remember, we had 4 gigabytes of virtual address, but in this example, we only had 256 megabytes of physical address. So that says these virtual pages have to be mapped into a smaller number of physical pages. So a whole bunch of these pages are going to have to be mapped to disk if we're using them. They're not all going to fit in here, but because we have the page table, we have the flexibility to change which ones are where. Here's another question. What would be true on a 32-bit machine, that is the virtual address or 32-bit, with 8 gigabytes of RAM installed? So before we looked at 4 gigabytes and 256 megabytes, but here we've got 8 gigabytes of RAM installed. So in this case, the physical address is going to be larger than the virtual address. So to address 8 gigabytes of memory, we need 33 bits, but we only have 32 bits for our virtual address. So here we're going to have a translation that looks a little bit different. We're going to take 20 bits of page number, put it into our page table, and transfer it to 21 bits of physical address. So what this says is that the whole program can fit in memory because we have more memory than our program can address. Our program can only address 32 bits of memory, but we have 33 bits of physical address space. So if we look at the other ones here, the page offset doesn't change. We still have 4 kilobyte pages in this case, and you could have whatever size you want, that doesn't change. The physical address isn't going to be the same size as the virtual address. The physical address is going to be larger. You would not need virtual memory. Well, if you're only running one program, you'd never need to page it out. But if you're running 2 or more programs, you could page it out, so you still need virtual memory.
Meet CodeRabbit, the AI-powered code reviewer. Get a comprehensive, context-aware code review within minutes.
Now let's walk through how we actually do this translation and what bits go where. So how do we do a page table lookup to translate from a virtual address to a physical address? So here's our page table, here's our virtual address, and our physical address. So our virtual address size is set by the ISA, and our physical address is set by the amount of RAM we have installed in the machine. So let's take a look at how this works. So the first thing we want to remember is we have this pages that are larger. So in this case we have a 4 kilobyte page, so we've got 12 bits for our page offset. So that means that these lower 12 bits, the page offset, they're not translated. They just go straight through. So that leaves us the remaining 20 bits of the virtual page number that needs to be translated into 16 bits of the physical page number. And how do we do this? Well, we're going to use the page table. So we take the virtual page number, we put it into the page table, we look up that virtual page, and then we get out the physical page that corresponds to it. So inside the page table, we're going to have an entry for every single virtual page, and for each of those virtual pages, we're going to have the physical page number, or if it's not in memory, something that tells us it's on disk. So each one of these is a page table entry. It tells us for a particular virtual page which physical page it's located at. And if you notice here, we have different number of bits. We have 16 bits for each of these entries. We have 20 bits for each of these entries. And that's because we have more virtual pages than we have physical pages, because we have less physical memory than we have virtual address space. All right, so let's take a look at how this works. We take our virtual page number, we go and find our entry, and that entry goes down to be our physical page. For the page offset, we don't change anything, it just goes through. So virtual page translated physical page, page offset untranslated, and the page table here needs to keep a mapping for every virtual page number. So remember, this is why it's important that we used pages. So now we have 1,000,000 entries here instead of having 1,000,000,000 entries here. Let's take a look at an example. So here are the bits. So the page offset is first 12 bits, then we've got the remaining 20 bits here. And down here in our physical address, we still got 12 bits here and the remaining bits here. Now we're going to translate this virtual address. So the first thing we do is we look at the 12 bits that are page offset. Those aren't going to be changed. They just go straight through. Then we can look at the remaining 20 bits that are virtual page number. So here's our virtual page number. We're going to take that, we're going to look it up here. Here's our entry in our page table. This is our page table entry for that virtual page number. We go ahead and select that. That's going to tell us what the physical page number is. Take the physical page number and get the result out. And so now this gives us what our translation is for this address. So the virtual address 0003.204 translated to 0006.204 for the physical address. Here's another one. So here's another virtual address, and here's a question about it. What do we get when we translate this virtual address? Well, here we're going to have to get it from disk. Because if we look at what the page table is going to do here, it's going to take the virtual page number here, which is 0, and if we look up virtual page number 0, it says it's on the disk. So let's walk through this. So the first thing we do is we take a look at our page offset here. Page offset's going to go through and it's not going to be changed, so it stays the same. Then we're going to look at our virtual page number. So our virtual page number here is all zeros. We go and look that up, and well, here's our page table entry for this virtual page number. And if we look at it, it says it's on disk. So we can't actually get a physical address for this because this data is on disk. We have to go to disk and load it. Now let's take a look at 64 kilobyte pages. So if we have 64 kilobyte pages instead of 4 kilobyte pages, how many bits do we need to use for the page offset? Well, we need to use 16 because 2 to the 16 is 64K. So we're going to use the lowest 16 bits here, so bits 15 through 0, and then now the virtual page number is just going to be the remaining 16 bits. Now we're going to have the same thing down here. The page offset for the physical address is now going to be 16 bits. We have even fewer bits for the physical page number. So if we go ahead and do a translation with this, we're going to have many fewer bits in here. So as we saw here we have 16 bits for the virtual page number, so our page table is now going to be indexed by 16 bits. So we've made our page table much, much smaller by making our pages larger. And then each one of these is going to have less bits for the physical page number because we have fewer physical pages. So by making larger pages, we have fewer entries in our page table, but we have to deal with data in a larger bunch. This now means that we have 64 kilobytes of data on disk instead of just 4 kilobytes the way we had it before. Now let's talk about page faults. So this is what happens when the data is not in memory and we have to go to disk to get it. So what happens if page is not in RAM? So first of all, how do we know if the page is not in RAM? Well, we know if page is not in RAM if the page table entry points to the disk. We can't have no entry in the page table because we have to have an entry in the page table for every address we could possibly access. And it's not a question if the address space doesn't fit in the physical address space, because if that's the case, some pages may or may not be on disk. We don't know which ones they are. So we need to know actually the page table entry. Here, this page table entry needs to tell us that it's on disk. So remember, we had the page table offset that goes right through, and then we had the virtual page number, and if it went here to a page table entry that was on disk, then we knew it was on disk. Now, what happens if it's not in RAM? Well, so the page table entry told us the page was on disk. Okay? Then the hardware, the CPU, is going to generate a page fault exception. This exception is then going to be picked up by the operating system. So the hardware causes the operating system to pick this up, and the operating system's page fault handler goes to clean it up. So now the operating system is responsible for figuring out which page wasn't in memory, figuring out where it is on the disk, and bringing it into memory. So the first thing the operating system does is it chooses something else to kick out of the memory. So if we need to bring more data into memory, presumably our memory is full, so we need to kick something else, and we're going to write that to disk. If the page is dirty, we need to write it back. So this page that we chose to evict, if the program has changed the data, we need to write it back. If it hasn't changed the data, it may be the same thing we had on memory before, so we don't have to write anything. That would mean it's not dirty. The OS is then going to read the page in from disk and put it into RAM. Then the OS is going to update the page table saying, hey, I've now put this data into RAM for you, so now you can use it. And then finally, the operating system is going to jump back to the instruction that caused the problem in the first place. So go back to the program and let it run. So now this second time when we go back, we're not going to have a page fault because we've loaded the page. Okay? So in this case, the only thing that's new here is this concept of dirty. If we have a page in memory that we haven't changed since we loaded it from disk last time, then we don't need to write it back to disk because we haven't changed it. But if we have changed it by writing to it, then we have to write it back. So how long does all of this take? Well, the answer is this last one, an amazingly, incredibly, painfully long time. Disks are so much slower than RAM that every time you have a page fault, it takes forever. In fact, when a program has a page fault, the operating system decides it's going to take so long to handle that it goes and finds another program to run instead, because it knows it's going to take forever for you to get your data back, and there's no point in having the program waiting. It's going to find some other work to do instead of your work. So, how long does a page fault take? So here are the things we're going to do. How long do they take? Well, how long does it take to find out if the page table entry says it's on disk? Well, this is really fast. We just need to look it up in the page table. How long does it take the CPU to generate a fault exception? Well, this could be hundreds, maybe thousands of cycles. It takes a while to generate one of these exceptions. How long does it take to jump into the operating system? This is actually really slow. This can take about 10,000 cycles just to jump into the operating system. So, okay, we know the data's on disk and we've taken 10,000 cycles just to get to the operating system. Then we need to write something out of RAM, take something from RAM and write it to disk to free up space. That's going to take a long time. That's going to take about 40 million cycles. A very long time. Disks are incredibly much slower than the CPUs themselves. Then we need to read in the data from disk and put it into memory. This is again going to take about 40 million cycles, a really long time to get this data. Then the operating system is going to update the page table to point to the new page. That may take about 1,000 cycles to do. It's going to be a while. You have to go through this big table and update it. Then the OS is going to jump back to where we were. And it took us about 10,000 cycles to jump into the operating system. It's going to take us about 10,000 cycles to get out. So if we add this all up, the time it takes to handle one page fault, you can do about 80 million cycles on a modern processor. So page faults are a real problem. In fact, page faults are probably the slowest possible thing that can happen to a computer except interacting with a human. I mean, humans are still much, much slower than page faults, but this is really slow. It's generally faster to go out on the network and get the data from another computer than it is to read it from your own disk. So page faults are very slow. And this is changing a little bit as we start getting these solid-state flash drives in computers, but they're still far, far slower, and people work really hard to avoid them. So, virtual memory and paging. Paging is one of those things you don't ever want to use, but it's good to have around. Why is that? Well, it's very, very slow. So if you have to page out something, it's going to hurt you a lot, but it's very, very good to not crash. So if we didn't have virtual memory, we'd crash if we ran out of memory, we'd have programs corrupting each other, all sorts of things. So paging in virtual memory is very important, but it's very painful. So if you have enough memory in your computer, you'll never need to page. And this is great. This is why buying more memory will make your computer faster. because if you're using more memory than you have, it slows things down. Now you'll note these two little caveats here. So you can never have enough memory. No matter what you do, you'll always find times when you're using up too much memory. The other thing is that some operating systems, they don't page out data to disk. So in the iOS operating system, used on the iPhone, if you run out of memory, the OS just kills your program. It gives you some warnings beforehand. It says, hey, you're about to run out of memory. Hey, you're really close to running out of memory, and then it just kills your program. And it's up to the programmer to make sure their program doesn't use too much memory. In Apple's operating system, OS X 10.9, to avoid paging out to disk, they compress your program first. So if there's not enough space in memory, the operating system will go through and find pages you haven't used in a while and compress them. So that's faster than writing out to disk is trying to compress the memory. So there are lots of ways to try and avoid doing this.
Precision Flag dulu, energinya nggak habis-habis. Hasilnya bombastis.
So now let's talk about memory protection, or some of the details about how we use virtual memory to prevent programs corrupting each other. So we saw this example before. If each program has its own page table, then we can match each program's virtual addresses to unique physical addresses, and it prevents them from accessing each other's data. So here's program 1 has its own page table or map here, program 2 has its own, and we saw how if program 1 tries to access virtual address 1024, its page table is going to send it somewhere else, maybe physical address 1 here. Program 2 also tries to access virtual address 1024, but its mapping, its page table, sends it to physical address 5, and these two things don't overlap. So let's take a look at this in a little more detail. So here's what the program address space looks like for a 32-bit Linux program. So each program has its own 32-bit address space, so each program sees the same 32-bit address space. Now, Linux defines how we use this address space. So the top 1 gigabyte of this address space is reserved for the kernel. So this is space that the program is not allowed to access, and it's for the kernel to store its data there. So the program can't read or write here, and in fact, if your program tries to access this, it'll crash. Then we have the stack. So the stack starts in here in the memory, and it's going to grow down. So the stack grows down as it gets bigger. Now remember, we used the stack when we were doing procedure calls. The stack is where you were storing registers, so you decrement the stack and it would grow down. This is where the stack is stored in memory. Then we have libraries in the middle here. These libraries are the shared data that we might have when we share with other programs. For example, if you have a save dialog box that's used by a lot of programs, it would be stored here. Then we have the heap. The heap is where the program allocates data. So if you're going to load a large image, the program is going to allocate a lot of memory on the heap. And the heap grows up. So when the stack grows down, and if it crashes into the libraries, or if the heap grows up and crashes into the libraries, that means you've run out of memory. So in addition to this here, we have 2 segments down at the bottom called the data and text. So the data segment here, this is the constants and data that your program has, and the text is the actual program. So this is the program code down here, or the program binary. And then finally at the bottom here, we have about 128 megabytes around 0 that are reserved basically for I/O, and the kernel doesn't let you get access to. So a bunch of space that's reserved for the kernel. We have the stack that goes down, the heap that goes up, libraries in the middle, and then we have our code and data for the program in the bottom here. There's something else that Linux does that's pretty cool. It puts random offsets in here. So your stack doesn't begin right at the end of kernel space. There's some random amount of space that's just wasted here. Then there's some random amount of space between the stack and the libraries, and some random amount of space between the data and the heap. And the reason for this is for security. So these offsets enhance security because you never know where your data or code is. So if I'm going to try and hack this program, so I'm going to try and write some data into it that makes it do something different, well, I need to write this down here in the actual part of the program that executes code. But if I'm up here somewhere in the stack and I've got this random offset, it may be hard for me to find that down there. Or if I want to write some code into the stack and then rely on something jumping back to it, well, if I don't know exactly where the stack is, it's hard for me to figure out where that jump is. So these random offsets here help reduce a bunch of different attacks that you can make on the program and improve security. So let's take a look at how these address spaces overlap in Linux. So here's 2 programs, program 1 and program 2, and they both have the same view of the address space. This is their own 32-bit virtual address space. And you can see how they map. So the kernel space on both of these maps to the same place in physical memory. That's fine. They're neither of them allowed to access it. Here in this case, we have the stack for program 1 mapping into here. We we have some of its libraries mapping into here, we have the heap from this program mapping into here, and maybe its libraries are mapping partially into here, so shared with the libraries from program 1, and some of its other libraries are down here. And so by doing this, we can use our mappings, or our page tables here, to allow these two programs to have the same view of their private virtual address space, but share the physical address space in a secure way. So here they can both share these shared libraries, but the stack for this program up here is not accessible from program 2's address space because it has no page table entry which will get it to this location. So we have these separate mappings that allow us to keep programs isolated, but we can also use these mappings to share data, as we showed here. So how do we provide these separate mappings? Well, the operating systems make sure you use the right page tables. So we have two programs here. They're both going to do a load to some location here, address 2 in this case, so virtual address 2 from both of these. They're both going to have their own page tables. They're both going to look up where virtual address 2 points to. They're going to get two different physical page numbers. So this one got a physical page address 4, it's going to find it over here, and this one got 9, it's going to find it over here. So they go ahead and access their data, and neither one of them is going to conflict because they get mapped somewhere else. And in fact, if you look through these page tables, you can see exactly how they're sharing the memory. So program 1 has physical page 1, 3, 4, and 6, so it gets 1, 3, 4, and 6. Program 2 has physical pages 5, 8, 9, and 2. So here's 2, 5, 8, and 9. It gets those ones. And both of these programs share physical page E. You can see that they both map virtual address FFFFF to physical address E. So that's the shared page down here. Now here's a question. I have two programs, and here are their page tables. And so which pages could these two programs access that would allow them to corrupt each other's data? Well, in this case, program 1 can access virtual page 2, which will go to physical page 4, and program 2 can access virtual page 1, which will also go to physical page 4. So in this case, these virtual addresses map to the same physical page. So these two programs could both access the same physical page, and they could corrupt each other's data. Or this data could be here because they need to communicate with each other. Think about if you're copying and pasting from one program to another. They have to be able to share that data somehow.
Lempar cel-cel di ongkir. Bayar ongkir di tempat, nggak bayar kalau telat.
So how do we make virtual memory work? And by making it work, that is, how do we get all those benefits we've seen and not have it slow down the computer? So we want virtual memory to be fast. So before we get there, let's think about exactly what we need to do when we have virtual memory. So for every single memory access, which of these things do we have to do with virtual memory? Well, we've got to access the page table in RAM. So we've got to go find the page table so we can get the information, the page table entry for the translation. So that's one memory access. Then we have to translate the address. So that's a bunch of operations. Then once we've got the final physical address, then we can go access the data in RAM. So we got to do at least two memory accesses here, one to the page table and one to the data for every access we want to do, plus all the work we have to do for this translation. So this is a lot of work. Remember, we have an average of 1.33 accesses for each instruction. Now we're going to have to do two memory accesses for each of those, and we're going to have to do all this work to translate it. So this is going to be very, very expensive if we try and do it this way. We got to figure out how to make it faster. So virtual memory is great. We saw this. We can do all this great stuff with it, but it comes at a very high cost. So every time we go to access anything in memory, if it's data or instructions, we have to look it up in the page table. We need the page table to get the translation from the virtual address to the physical address. So we need to first access the page table, then after we access the page table, then we do the memory. So we've now doubled our number of memory accesses due to virtual memory. So this is going to be a real problem here. How can we make a page table lookup really, really fast? So we need most of the time, when I do a page table lookup, that it has to be basically instant. Can't slow down my memory access. Can't do this in software, so we don't afford an extra 5 instructions and a memory access to do the translation. That would really slow everything down. So we're going to have to do this in hardware. We're going to have to build a cache for the page table. So something in hardware that keeps a bunch of the page table around so we can really quickly do the translation. So how do we make virtual memory fast? We use what's known as a TLB. It's a page table cache called the translation look-aside buffer. It's a little buffer on the side or a cache that we look into to see what's the translation for this address. So our processor is going to output a virtual address, and our memory needs a physical address. In order to make this fast, we have to put something in the middle here. So remember, our full page table is going to sit over here in memory, and we've got about 1 million entries for our full page table, and each one of them is about 4 bytes, so it's about 4 million bytes or 4 megabytes for our page table. Now, if the processor just tries to go access the page table directly and load back the entry to do the translation, this is going to be too slow. This is how we end up with an extra memory access for every single access. So what we need to do instead is put in a little cache, and this is exactly what we're going to do. We're going to put in a TLB, or a translation look-aside buffer, in the middle here. This is going to be really small, but also really fast. So it needs to be fast because we do this on every memory access. So typically it's about 1 cycle or less than a cycle to access that, and it's very similar to a cache. So the TLB, if it doesn't have the data, we're going to go to the page table and we're going to load the data into the TLB, just like a cache. And this is slow, but once we've got the data in the TLB, we can do the translation very quickly. So we can do this fast translation to go directly from the processor to the address in memory. So to be fast, however, we need to make the TLB really small. And to make it even faster for instructions and data, we can't use one TLB, so we tend to have one TLB, the instruction TLB for instructions, and a separate TLB, or the data TLB, for the data. On modern processors, like Intel processors today, TLBs are really small, so 64 entries, 4-way, not very big, reasonably high associativity, and this is what you get for 4 kilobyte pages. If you go up to larger pages, 2 megabyte pages, you don't actually get the same number of entries. You get fewer entries in it, but you still have it being 4-way. So remember here, the page table has 1 million entries for a 32-bit program, and I'm telling you that the TLB has 64 entries. That's a tiny fraction of the total amount of entries in the program. So you're going to realize that we're going to spend a fair amount of time updating the TLB with the current entries. Now, the reason this works well is you have lots of locality. Remember, each one of these entries covers 4 kilobytes of data. So as long as my program is somewhere in this 4 kilobytes of data, I'm going to be just fine with that page table entry for a long time. Now, what can happen if we go to access memory? So this is the setup we've got here. Our processor is giving us virtual addresses. We go to our TLB to try and do our translation. Gives us our physical address. We go to memory. If it's not in the TLB, we're going to have to go get it from the full page table. So there are 2 things that can happen. Our page can be in RAM. So if our page is in RAM, the worst that happens is we have to go to the full page table to get the page table entry so we can find it. But bad things can also happen. What if our page is not in RAM? Well, if our page is not in RAM, it's out on disk here, and we know that's going to take a really long time to go access. Now, if the page is RAM, we have 2 things that could happen. We could have our page table entry in the TLB, so this cache of page table entries is working correctly. In that case, we're going to access it really quickly. Going to go directly from the processor to the TLB to the memory. So this is going to be really good performance. This is what we want almost all the time, so really fast. You can also have it where the page table is not in the TLB, and this gives you pretty poor performance. So if it's not in the TLB, then we have to go all the way to memory, find one page in the page table, and load it into the TLB before we can go and do our translation. And this is going to take anywhere from 20 to 1,000 cycles on a modern processor. So this is slow. This is really painful. And you might say, well, hey, it's only 20 cycles or so. But remember, we have 1.33 memory accesses for every instruction. We can't afford this very often or it's going to destroy our performance. So these are the good cases where we have the page in memory. Now for the bad cases, we could have the page table entry in the TLB. Now this is unlikely. And it's unlikely because if we've evicted the page to disk, chances are we haven't used it for a long time, so its TLB entry's probably been evicted as well. But if it is in here, then okay, well, we find out really quickly that it's going to take us forever to get it from disk. The other option is that the page table entry is not in the TLB and we have to go to the full page table before we find out it's on disk. So this case is horrible. This case over here is just slightly more horrible. Not really much of a difference between horrible and slightly more horrible. So in both of these cases, we're going to spend millions and millions of cycles trying to get it from disk. In this case up here, where the page is in the TLB, well, we're going to get it pretty quickly. We're going to know in one cycle that it's going to take us a ridiculously long time to get it. In this case over here, it's going to take a while, before we realize it's going to take a ridiculously long time to get it. So basically, if the page is not in RAM, it doesn't matter if it's in the TLB or not, because you're going to spend so much time trying to go get it from disk. So, what can we do to try and make our TLBs seem bigger? So we said the TLB here is really small. What can we do? Which one of these things here will make it seem bigger? Well, several of them. So the first one here is making pages larger. So if we have a TLB here, and it's using 4 kilobyte pages, so this is what we have on most Intel processors, 64 4 kilobyte pages, that means that the TLB can cover 256 kilobytes of data. So if you use all the pages in the TLB, it can translate enough addresses to access 256 kilobytes of data in your memory. Now if we change this, so instead of having 4 kilobyte pages, we have 2 megabyte pages. So this is the other option with Intel processors. You have 32 2 megabyte pages. Now we can cover 64 megabytes of data. So by using a larger page here, we can cover enormously more data without having to bring new things into our TLB. So making the pages larger allows us to reduce the number of accesses we have to have, reduce the number of times we miss in the TLB because the TLB can reach more data. We can also add a second TLB. So most processors do this. They have a much larger TLB, about 8 times larger, but it's also about twice as small. So go ahead and put in a second TLB in here, and if we don't find the data in the first TLB, let's go search in the second TLB. This is still a lot faster than going to the full page table in memory, but it's a lot slower than accessing our first TLB. And finally, we can have hardware that fills the page table. So instead of having to go into software here and have software walk over to memory, we can put a little bit of hardware on our processor, and we miss in the TLB, the hardware will automatically go to the page table and will automatically load the results into the TLB. And so Intel processors, for example, support this. And this allows you to do page table refills, getting new data for your TLB here, faster than having to switch to the operating system and let the operating system do it.
Flash sale mobil 11.000 dengan SPay Later di Shopee. 11 November jam 12 tengah malam.
Let's take a look at an example of how the TLB works. And if you've seen caches, you'll remember that this looks an awful lot like a cache. So here's our setup here. We've got our virtual address, we've got a page offset and a virtual page number. We're going to use our TLB, which is going to have a tag and a physical page number, to translate the virtual page into a physical page and give us our physical address. So let's go ahead and get started. Here's a virtual address that comes in. We look at the page offset. The page offset is just going to go right through. And we have a virtual page number. The virtual page number is going to be translated. So the page offset just gets passed through. The virtual page number is going to go into the TLB, and well, there's nothing in our TLB yet. So it's not in here, so we missed in the TLB. Now we need to go look up in our page table in order to get it. So we're going to have to go load from main memory to get our page table, and here's our page table, and it's in main memory. Now remember, the page table has to stay in main memory all the time, or we'll never be able to access anything. So we've got this in main memory so we can access it. Now we go ahead, we look up in our page table here. We want to find virtual page 3. So here's our page table. We're going to go down and look at page 3 in our page table. Here's the physical address or the physical page number we need. So we go ahead, we fill this into our TLB. So it's page 6, physical page, and our tag is 3 because we're looking virtual page 3 maps to physical page 6. Now we've loaded this into our TLB, and now we can go ahead and do our translation. So here we get our physical address. Now, here comes another one. So here's our virtual address 0003208. So again, we've got a page offset and a virtual page number. Page offset goes straight through. The virtual page number is going to go look up in the TLB. This time we're going to have a hit in the TLB because we actually have an entry for this. So we'll get the translation immediately. This is the best case. We found our virtual page in the TLB, and we immediately got a physical translation. Here's an example of missing. So we go to access this virtual address here. Now, the page offset's fine. Here's our virtual page number. Page offset goes straight through. The virtual page number goes to look in the cache. Well, sorry, not in the cache, the TLB, which is a page table cache. We look in here, it's not in here, so we're going to go over to memory and load this. We go to our page table in memory. We're looking virtual page 5, so we're going to walk 5 entries into our page table. Here's our translation. We take the translation, move it into our TLB, set the tag correctly so we know which virtual page this refers to, and now we can do our translation. So here's an example. We have a hit in the TLB. So we're going to go ahead and access this address here. When we run this address through the TLB, we find, hey, the data's in here. Great. So we've got our data. Now let's see what happens with this address. So here's a virtual address 4200. So our page offset's 200 and our page number is 4. So the page offset goes right through, and the virtual page number is going to go look in the TLB, but we don't find it in the TLB. And our TLB is full. So we're going to have to figure out which one of these entries to kick out. So in this case, we're going to kick out the one that we used least recently. Remember, we just used this entry, so we'll kick out this entry here. Now we go over the page table. We find our page table. We're looking for virtual page number 4. So we walk down to virtual page number 4. Here's our translation. We bring our translation over, we install it, and we go ahead and use it in order to do our translation. Here's another one. So what's going to happen when I do this? So here's an address, 0000860. What's going to happen when we do this translation? Well, in this case, we're going to have a TLB miss, because if you look up here, we don't have virtual page number 0 in our TLB, and then we're going to have to evict one of these things. And then when we go to load it, look over here, our first page in our page table says the data's on disk. So we're going to have to go to disk. So let's walk through this. Here's our page offset, it goes straight through. Here's our virtual page number. We look in our TLB. Yeah, it's not in the TLB. Okay, fine. So we're going to evict one of these. So we go ahead and evict it. And we're going to go to memory to load it from memory. So we go to our page table. We're looking at virtual page 0. So that's going to be the first page in our page table. We find it here. We load it in. And hey, it says it's on disk. So now when we try and do our translation, we get a page fault. And we have to wait a really, really long time to get the data from disk. Let's talk a little bit about the size of the page table. And this is important because we've mentioned that, well, we need 1 million entries for our 32-bit page table, and they're going to take up a fair amount of memory. So for a 32-bit machine with 4 kilobyte pages, this is what we've been talking about sort of as the default, we need 1 million page table entries. So we figured this out. We have 32 bits, but we have 12 bits of page offset, so we have 20 bits of address we need to translate, so 2 to the 20 is 1 million page entries. We also said that each page table entry is about 4 bytes. So we need about 20 bits for the physical page, we need some miscellaneous permission bits and the like. So what does this work out to? Well, it works out to 4 megabytes total. So we need 4 megabytes to store a page table. Okay, that doesn't seem so bad, except each program needs its own page table. Remember, each program needs its own page table because each program has its own translation from its own virtual address space to the physical address space. So if we have 100 programs running, which is very typical of computers these days, we need 400 megabytes of memory just for the page tables. That's a lot of memory just to keep track of where those programs have memory. And here's the hard part about this. We can't swap the page tables out to disk. So if we're not using them, we can't write them out of disk to free up space. And the reason for this is if the page table's not in the RAM, we can't access it, so we can't find it. So there's no way to find the memory for a program if we can't access the page table, because we need the page table to do the translation. So how can we fix this? Well, remember how we fixed the problems with memory in the first place? Remember what virtual memory did? So virtual memory was a level of indirection that we added, and well, we can fix this problem with more indirection. Let's take a look at that. So what we're going to do is have multi-level page tables. So we're going to have a first level page table, and our first level page table is going to be 4 kilobytes, and it's going to have 1024 page table entries. So it's going to point to 1024 other pages. Then we're going to have a second level page table, and each one of these is going to have 1024 entries. So if we need to access something in this part, this isn't actually pointing to a memory translation, it's going to point to another page. And this page is going to be another page of page table entries. So what we're saying is that this whole bunch of page table entries is pointed to by this page table entry. And this one's going to point to another bunch, and this one's going to point to another bunch. So now I've got 2 levels in our hierarchy here. So in the memory over here, we're going to have to store this in the memory. So we can take a look at this. What this says is this first level page table tells me if I need to access any of this data, go look up where exactly it is in this page table off in memory. And here's how you find it in memory. If I need to access any of this data, well, it's in this part of the page table off in memory. And if I need to access any of this data, well, it's off on disk. So by having this first and second level, these multi-level page tables, we can start paging out parts of our page table. We no longer have to have it in memory all the time. So the second level page tables can be paged out because we can always find them. We can use the first level page table in order to find it. Now the first level page table, it has to stay in memory. because we need to be able to access this so we can find the other page tables. Okay, so this gets us to the point where we just need to have one of these pages in memory and one other one in order to access the actual program memory. So in a multi-level page table, what's the smallest amount of page table data we need to keep in memory for each 32-bit application? We're assuming 4 kilobyte pages here. Well, I kind of just gave you the answer for this. So it's 4 kilobytes plus 4 kilobytes. We always need the first level page table because the first level page table lets us find the second level page tables. But if we want to actually do anything with the program, we need both a first level page table and a second level one, at least one, so that we can do some real translations. So we need one first level page table, 4 kilobytes, and one second level page table, 4 kilobytes. So the minimum amount is 4 plus 4 kilobytes, or 8 kilobytes per program, which is much better than 4 megabytes per program if we have to keep the whole page table in memory. So here's our memory. We need to have at least our first level page table, and that's going to point to at least one second level page table, and we need both of these in memory at the same time so we can actually do any translation. Now let's take a look at how we actually do the translation with a multi-level page table. So here's our virtual address that we're going to translate. You can see over here in memory we have our first level page table entry and we have some second level page table entries. We're going to go ahead and translate it. These are the page offset bits, and we know they just go straight through. Now we're going to look at our virtual page number. So here's our virtual page number, but now we're going to divide it into two parts, one for each level. So we're going to take the top bits of the virtual address, and we're going to call this part the one that go into the first level table. So here are the first 10 bits of our virtual address, and we're going to use those to look into our first level page table. So that tells us that we're going to need to go get our second level page table at physical address 003. So we go and take that address, we go get our second level page table from memory, and remember this can be on disk if it's pointed that way. We take the second level page table, we load it into memory, we access it, and now how do we figure out which one of these pages we really want? Well, we're going to take the rest of the bits here. So we've got the rest of the bits of our virtual page number here, another 10 bits. These 10 bits are going to tell us, oh, we want this entry here. Now once we've got that entry, that gives us our translation. So the multi-level page table, we take the top 10 bits here and use that to figure out which one of the entries in our first level page table we want. That tells us where to go for our second level page table, and it can also tell us on disk. That's what allows us to page out page tables. Once we have that, we go into our second level page table and we use the next 10 bits of our address to find the particular entry which gives us our translation. So to make these page tables look, we have to keep our first level page table memory at all times so we can find the other pages, and we need at least one second level page table in memory at all times so we can do actual translations. Because remember, it's this table which gives us the translations for the program. So how do we use them both? We divide up our virtual page number. We send some of the bits to choose the entry in the first level table and some of the bits to choose the entry in the second level table. The benefit of this, now we can page out parts of the page table so we don't have to keep it all in memory for every program all the time. So here's a question. If I'm running 100 applications on my computer with a 2-level page table, how much memory do I have to keep in RAM at all times to access all the applications, be able to access their data? What's the minimum amount I have to keep in memory at all times for their page tables? Well, in this case, it's 800 kilobytes. So for each application, we need its first level page table and at least one second level page table so we can get some translation. 100 applications, that's 100 times 8 kilobytes or 800 kilobytes. If we'd had to keep the whole page table in memory, this would be 100 times 4 megabytes or 400 megabytes. So we're saving a huge amount of space by doing this.
Aku punya kejutan.
Burger King Spicy Chicken barunya.
Pedasnya nagih sampai gigitan terakhir.
Now let's see how TLBs and caches interact. Since they both have to do with accessing data and addresses, they've got to be pretty tightly coupled. So there are basically two ways that we can put TLBs and caches together. We have our CPU generates a virtual address. We can take that virtual address, put it into the TLB, we'll get out a physical address, then we can take that physical address, put it into our cache, and if we're lucky we get a hit and we return it to the CPU, and if we're not lucky we get a miss and we go to our memory. So this is sort of the straightforward way to do it. First we do our translation, then we do our cache lookup. This is called a physical cache because our cache uses a physical address. Now physical caches are simple but they're slow. This is the real problem. We have to do this TLB lookup before we access the cache. So if this takes about 1 cycle and this takes about 1 cycle, it's now going to take us 2 cycles to find data in the cache. The other way to do this is a virtual cache. So we take our CPU, which is going to give us a virtual address, and we connect that directly to our cache. Now our cache is going to look up data based on the virtual address. So if we have a hit here, we return it to the CPU. And this is really fast because we don't have to do any translation. We just go directly to the cache. Now if we miss in the cache, we've got to go to DRAM, and DRAM's physical address. So if we have a miss, then we're going to go to the TLB, translate to a physical address, and go to DRAM. So the virtual cache is fast. We only have to do a TLB lookup when we miss in the cache, and well, we know if we miss in the cache, it's going to take a long time to go to DRAM anyways, so this sounds like the right way to do it. Now here's a question. Can I have 2 programs share a virtual cache? Well, not really. And this is the problem with virtual caches. So the virtual cache here is storing the program by the virtual address. There's no translation. So I can't run 2 programs on my CPU and keep their data separate. If I have 2 programs that are running here, they're both outputting virtual addresses, and there's nothing to prevent those 2 virtual addresses from colliding in the cache. So if program 1 access address 1000, that's a virtual address, it'll go look up address 1000 in the cache, and if program 2 runs on the CPU and accesses virtual address 1000, it'll also find virtual address 1000 in the cache. Because there's no translation before I access the data in the cache, there's no way to keep the applications apart. So this is the problem with a virtual cache. Now there are ways to work around this. So you can have a separate bit in here so that I don't just send the virtual address, I send the virtual address plus a special bit which tells me which program it is. Or every time I switch programs on my CPU, I can flush out all the data from the cache. So you can make this work. And it would be great if we could make this work because this is a lot faster. I don't have to wait for the TLB the way I do in the physical cache. Now, can we get the best of both worlds? So can we access the cache at the same time as the TLB but still have the protection of the virtual memory? So can we go straight to the cache without having to wait for the TLB but still get virtual memory protection? So the idea here is we're going to look up the data in the cache with the virtual address, but we're going to verify the data is right with a physical tag. So remember, when we look up data in the cache, we get the tag out, and the tag tells us is it the right address. So we're going to use the tag as a physical tag, but we're going to look up by the virtual address. So here's our cache. We're going to use a virtual index, so straight from the CPU, virtual address, to look in the cache and find the right cache line. Then we're going to get out the tag for that cache line, but the tag is going to be a physical address. So in order to see if this is the right data, we're going to take that physical tag, we're going to take the physical address from the TLB, and we're going to compare them to see if we have a hit or miss. So the benefit of this is I can start looking in the cache right away with the virtual address from the processor, and at the same time I can go start doing the translation so that when I'm done looking in the cache, I have the translation and can see if there's a hit or miss. So this is called a VIPT, or virtually indexed physically tagged cache, and this is the most common sort of level 1 cache used in processors today. So the key here is the data is indexed by the virtual address, so we can right away start looking into the cache, but it's tagged by the physical address. So we can look at the TLB in parallel, and we're done with the TLB, we can see if we get it, but because it's tagged by the physical address, we get all the protections of virtual memory. So we only get a hit, that is, we're only sure it's the right data, if the tag matches with the physical address, so that means that we get all these wonderful protections. Now, let's take a look at this. So here's my CPU, and it's going to output a virtual address. I've got my cache over here, and I want to have a cache return the value as quickly as I can. But my cache is going to have physical address tags. So that means in order to know if the data is correct in the cache, I'm going to get out a physical address tag. To compare this, I need to know the physical address I'm trying to look up. In order to get that, I have to use the TLB. So now we want to do these two things at the same time. We want to look up the TLB and the cache at the same time. So in order to do that, we take our page offset, and we use the page offset to index into the tags on the cache, and we use the virtual page in order to look in the TLB. So now we're using part of our bits to index the cache right away, part of our bits to index the TLB right away. We run the TLB at the same time as the cache, and then we compare them at the end here. So this is great. Now we've gone and we're comparing based on the physical address, so we're guaranteed to get all the protections of the TLB, but we're looking up very quickly based on the offset here, which is the same for the physical and the virtual address, so we don't have to wait for the TLB to start looking in the cache. So in a VIPed cache, we're doing the TLB translation and cache lookup at the same time. TLB at the same time we do the cache. We use the virtual page to do the TLB and lookup, and we use the page offset bits to look into the cache. So the TLB is going to give us the physical page, and the cache is giving us a physical tag, and then we just compare them at the end. And we're doing a physical address comparison, which means we get all the benefits of the TLB. If it turns out that the virtual address, the offset here we use to look it up, is for another program, then the physical tags won't match, and we'll say it's a miss. So this has the benefits we want. This is fast. We don't have to wait for the TLB before we look in the cache. We can look in the cache right away and look in the TLB at the same time to see if we get a hit. But it's also safe because we compare the physical address tags, so we're guaranteed to only get a hit if it's really the right physical address for our program. Now, there's a caveat here. If you look at what's happening here, I can only use bits that aren't part of my virtual page in order to look into the cache here. So I can't make my cache infinitely big because I can only have a certain number of bits to index into it here. However, despite that, most processors use this today. So this is the most common sort of level 1 cache used in processors today. So let's take a look at this limit a little bit more. So if I have 4 kilobyte pages, how many bytes can a direct map, that is one-way, VIPed cache store? Well, it can only store 4 kilobyte. Well, if I have 4 kilobyte pages, that means I have 12 bits for this page offset, so I only have 12 bits that I can use to index into my cache. So I only store 4 kilobytes of data. That's not very good. But if we increase the associativity, we can do better. So if I make it an 8-way cache, then I can have 8 times as much data. So I could have 32 kilobytes. And that's because each way is using the same index, we just have different tags for them. So this is a real limitation of VIPed, and this is one of the reasons you don't see very large level 1 caches.
Hi guys, so if you are from Indonesia and if you want to work remotely and earn one...
So now let's summarize what we've seen in virtual memory here. So virtual memory is fundamentally a level of indirection, and it's indirection between the virtual program addresses that we give to each program and the physical RAM addresses that we have in our memory. By adding this level of indirection, we can do a lot of cool things. So we can map memory to disk, so it gives us sort of unlimited memory. We can keep programs from accessing each other's memory. This gives us security and reliability, and that's because each program has its own virtual addresses. So they each have their own 32-bit address space. We can also fill holes in the memory address space, so this gives us efficiency. Because we've got this mapping between the program addresses and the physical addresses, even if we have holes in our physical addresses, we can just map some more programs into it without any problems. However, the trade-off here is we have to translate every single memory access. So all of our programs are going to give us virtual addresses, we have to translate them to physical addresses. And remember, we have 1.33 memory accesses for every instruction, which means we need to be able to do this really fast, not hurt performance. So in order to keep track of these translations, we have page tables. And the page tables keep track of all of the translations for a program. So that's a lot of entries. And in fact, if we want to translate every word, it's going to be a whole large number of entries. We need one word translation for every single one of our addresses in the program's address space. In order to solve that problem, we use larger pages. So today we use 4 kilobyte pages. People are moving to even larger pages. And this allows us to reduce the number of page table entries in the page table. So with 4 kilobyte pages for a 32-bit machine, we only need 1 million page table entries. In order to make this fast, we have a hardware translation look-aside buffer, the TLB, which is a small cache which keeps the most recently used page table entries in order to do really fast translation. So we also saw how we need to be able to work with the TLB and the cache together for good performance. We saw 2 basic caches, there were basic combinations. There was the physical cache. So the physical cache has a physical address into the cache, which means we have to do the translation first. So we have to wait for the TLB before we can access the cache, and this is slow. We also saw virtual caches. So virtual caches use the virtual address directly. We don't need any translation, but because we don't have any translation, we don't get any protection. So we don't get the security to prevent programs from bumping into each other. we then saw the combination of a virtually indexed, physically tagged, or VIPed cache. So the VIP cache uses the virtual address for the index and the physical address for the tag. This allows us to look up data in the cache using the virtual address at the same time as we run the TLB, and then at the end we use the physical address to make sure that we're not having any security problems. So this is a very common way to do things, but it limits the size of our cache because we can only use the bits that are the same between the virtual and physical address in order to index into the cache, so it limits its size.
Hi everyone, I welcome you all to the live session on Data Analytics full course by IntelliPad. This session is conducted by multiple experts who will be teaching you all about data analytics from basics to advanced level.